Our next speaker is Dmitry Levkov from the Institute for Nuclear Research of the Russian Academy of Sciences, and he's speaking on semiclassical S-matrix and black hole entropy in dilaton gravity.
Okay, I wish to thank conveners for inviting me to give a talk, and today I'm going to discuss something well, entirely different, in fact, from previous two talks, and that will be S-matrix for gravitational theories and their relation to black hole physics. And this talk is based on two papers with Maxim Fetkevich, Sergei Siberyakov, and Igor Zenkevich during last year. My motivation is, of course, an information paradox, and which is an apparent unitarity loss in certain processes. Namely, let us start with a multi-particle state, say a coherent state with many particles, and assume that they move together towards one point, they contract, and with time they should form a black hole. And as Hawking showed like 50 years ago, the black holes is not the final states of these processes. They evaporate and they produce a thermal bath of particles in the flat space again. So, and these particles naively should be described by density matrix, by thermal density matrix. But this means that overall we have a transition starting from the coherent state, from the pure state, via the black hole to the density matrix, and this is forbidden in quantum theory. So this suggests a non-unitary, apparent non-unitary evolution. But now we know, now there are strong arguments, okay, based on ADS-CFT correspondence, that this is actually related to some like small errors in the calculation, small things that are not taken into account in the calculation. And in fact, the final state is pure. And the main argument is ADS-CFT, of course, which states that the quantum gravity on certain background on ADS-5 across S5 equals to the unitary and healthy CFT. And black holes are thermal states in there. And this means that actually the process, the overall scattering process starting from particles and ending up with Hawking quanta should be unitary. Actually, last 2 years, there appeared a confirmation of this by people. Many people have calculated the entanglement entropy of the final state particles, and this new entanglement entropy showed that these states, final state is pure, in fact. So the overall process, actually, if we forget about the black hole in the middle, is transition from particles in the flat space-time, from Fock space state psi in to the Fock space state psi out. So this transition is a scattering process that should be described by an S-matrix. So the next question is, what is the S-matrix for this process? And if we manage to calculate, so in this talk, I will consider precisely this S-matrix of this complicated scattering process. And if we get the S-matrix, eventually we will be able to check a unitarity of this S-matrix directly. And I will comment on this in the end. So consider first a scattering process which doesn't involve the black holes. So this is just the usual scattering process. How do we describe it semiclassically? I will assume that there are many particles in the initial state and many particles in the final state. I can write an S-matrix element like any element in the theory in the form of the path integral. Path integral goes over the metric, over matter fields, over ghosts, whatever. And the integrand involves the classical action and the initial and final states. Everything I compactly denote by S total. Okay, so we can always write a path integral for any scattering process. And if there are many particles inside, the integrand actually oscillates very fast. So it can be evaluated by the saddle point method. the method is very simple. We should find a saddle point configuration extremizing the classical action, the integrand actually.
Excuse me, Dmitry.
Okay.
There are people in the chat that says that they can't hear you properly, and can you please increase the volume of the microphone?
Okay, so sorry about that. Okay, so I actually can increase the volume of my microphone, so it's on the maximum. So I hope that it's okay now. Okay, let me proceed. Yeah, so we can always compute any matrix element of S-matrix by saddle point computing the path integral if there are many particles involved. And this is perfect for the processes of black hole formation and evaporation. Seems perfect. Once we compute the saddle point configuration which extremizes the integrand, then we can get the amplitude just by substituting the saddle point into the integrand. So I to the S total evaluated on the saddle point gives you the amplitude. Okay, let us try to perform the procedure for the collapsing case. So we consider particles which have which move together into one point, and classically they should collapse. And this is the initial state of the process. And we try to solve the Einstein equations coupled to the matter equations. And actually, there is a theorem saying that the classical solutions in this case starts from particles in the flat times and ends up with black holes. And this is not a correct saddle point solution. Let me explain. In the path integral for the S matrix, all configurations you integrate over, you integrate over only the configurations which start from waves in the flat space-time and end up with waves in the flat space-time. So all these configurations describe scattering processes. But collapsing solutions end up with black hole and do not go into the out state. In this sense, they have incorrect asymptotics. They do not belong to the class of configurations, required class of configurations, and we cannot use them as a saddle points. So this will not do. We shouldn't use them. The question is whether there are complex saddle point configurations and how to find them. And here's the method. Our method to find the complex saddle point configurations. And to understand the method, you should first imagine that we can voluntarily change the Einstein equations. So we cannot actually, but let me add a constraint to the Einstein equations. Let me define a functional which measures the mass inside some large sphere integrated over time. So for scattering configuration, we describe particles goes into the sphere, scatter and out of the sphere. This mass integrated over time will be finite. If the particles go in and form a black hole, for such solution, the value of this functional will be infinite. So I add this constraint on the level of the action with Lagrange multiplier, and this changes the Einstein equations. But this constraint guarantees T int equals to T naught, guarantees that the solutions of this new theory will have correct asymptotics. So the particles will go in, scatter, form something similar to black hole, but not a black hole, and go out. But this, of course, happens at the price of incorrect equations. And let me summarize the properties of the functional that I need of the constraint functional. It should be positive and reparameterization invariant. It should be infinite if the configuration describes formation of black hole. And it should be finite if the configuration describes scattering and particles go into the sphere and out of the sphere. And now the main trick of this story is as follows. Let us start from the path integral for the amplitude, the old path integral from the beginning, and insert a unity integral over dt naught of delta function of t naught minus t. So this is a unity on one hand. On the other hand, we will calculate first the saddle point integral over all configurations except for t naught. And inside this path integral, in the integrand, we have a delta function that ensures that t equals to t naught. So these configurations, saddle point configurations, and the configurations over which we integrate, they automatically satisfy this constraint, and they automatically describe scattering process. Technically, yeah, in the end, we'll integrate over t naught. Technically, it is convenient to use a Fourier representation for the delta function, and this gives the exponent in the integrand, and just with the new modified action, S epsilon equals to S total plus I epsilon tint. Epsilon is deformation parameter. And the new regularized configurations will be a saddle point configurations of this new functional, and they should have correct asymptotics. And actually, in the end, we integrate take saddle point integral over epsilon t naught. And this means that actually you can show that the saddle point equations for epsilon and t naught, that epsilon should go to 0. So this is really a regularization. We first add a term to the action, and then we send the coefficient in front of this term to 0. But at any non-zero epsilon, we should get a configuration that describes scattering. There is another bonus in this story. The thing is that this new artificial functional is positive definite. This means that we can deform the analytically continue value of epsilon to I epsilon here. And this means that we can, and this makes the integral better convergent. And this means that we should add a complex term to the action, and epsilon goes to +0 means that this term is purely imaginary and vanishing. And in the end, yes, so the price to pay is just one additional limit. And in 2015, we were applying this this method to a simple model of shells in 4-dimensional gravity. And now I will apply the same method, and quite successfully, yeah. And now I will try to apply. I will apply the same method in 2-dimensional dilaton gravity. Here's the 2-dimensional dilaton gravity. It consists of the bulk action describing two fields: the scalar dilaton and metric G mu, 2-dimensional metric G mu, and it has one mass scale lambda. Okay, and this is just the CGHS model, which is quite popular model of dilaton gravity. But we modify this model, and I will explain why later. And we add a boundary to the space. So this boundary cuts all region with positive phi, and the physical region is a region where phi is negative. And this actually means that the spatial coordinate doesn't live on the whole line. It lives on the half of the line from R0 to infinity. And of course, we should add a boundary Gibbons-Hawking term to this. And so this is the model of gravity defined on the half of line. And I will consider a very simple matter in the form of one quantum particles with mass m. And here's the action of the particle. And there are good properties of this model which make it suitable for us. It has exact solutions and stable vacuum. And it has black holes. And lambda, actually the parameter in the action, is exactly the black hole temperature. And in Schwarzschild coordinates, black holes have Schwarzschild radius of the horizon, which is larger at larger masses of black holes. That's it. So black holes are just standard, and we can describe our process. Just I owe you an explanation. Why did I introduce the boundary in this model? Why did they modify the model to lie on the half line? And the reason is that we cannot just consistently quantize the CGHS model on the whole line. And the reason is as follows. Suppose we have a path integral for the CGHS quantized, defined in the most, most standard way accepted in the literature. And suppose we perform a singular Weyl transformation, just change metric by some factor depending on dilaton field and change dilaton. And we get this. And this is another model, very simple model. The action is here in the integrand, and this model is called Jacob-Teitelbaum gravity, actually flat limit of Jacob-Teitelbaum gravity when the cosmological constant in this Jacob-Teitelbaum gravity goes to 0. I just warn you that this Weyl transform is anomalous. So during this transform, functional measure changes, action changes, everything changes and leads to JT model. So the problem is that the JT model is unitary and is perfectly healthy. So we make a absolutely sick transformation, which is singular at certain value, at certain line where phi, the dilaton field, equals to phi critical. And we obtain a unitary and perfectly sane model. And this means that the model we started with has a singularity, and this singularity can be just reduced by correct quantization. Correct quantization is quantization of the JT model. And our solution to this is as follows. We cut half of space, define the model on the half line, and this cuts this singularity at phi equals to phi critical, but introduces instead a boundary, a dynamical boundary. And so our model has one particle and one boundary. So now let us send particle from the right-hand side to the left-hand side towards the boundary. It will scatter off the boundary and it reflects from it and goes to infinity again. So this is the reflection amplitude where a particle changes its momentum to minus p. And the energy of particle will be denoted by large letter m. And of course, this amplitude is given by the path integral where integration goes over metric, dilaton, and particle trajectory. By taking the saddle point, solving the saddle point equations for S total, we get the classical equation for the saddle point configuration. And yeah, these are the classical equations. And let me describe the solution to this equation. So this slide explains the simple solution to these equations. I will work in Schwarzschild coordinates. This means that, R is the Schwarzschild coordinate, which starts from R0, the boundary, and extend to plus infinity. And actually, they are valid analog of Birkhoff theorem that the solution of these equations in empty space where, in solution in empty space is either flat or this is the Schwarzschild solution of mass m. Okay, there are no other solutions. So there is a particle at position some position r star. So inside the to the left of the particle, the space should be flat, and to the right of the particle, the space should be Schwarzschild, and with mass m. And m is the gravitational mass of this particle. That's it. Simultaneously, this is the total energy of particle. And particle moves towards the boundary and reflects from it. And so if you write down the equations near the position of the particle, you get the equation for the particle trajectory. Okay, so here are the classical solution. That's how they look like. At low energies, particle just starts from infinity. It goes towards the boundary, reflects from it, and goes out. Of course, the outer metric of the particle is a Schwarzschild, and Schwarzschild metric has formally always the Schwarzschild radius. But this radius, the value of this radius, is somewhere to the left-hand side of R0 in the unphysical region. So the whole solution is not singular, it is okay. But if energy is higher than some critical value, just the horizon is to the right hand side of the boundary. So the particle goes in, it goes under its own horizon, it reflects from the boundary probably, but it cannot go out of the horizon. So it stuck in there, and so the black hole is formed. And this is the solution which has incorrect asymptotics, and it doesn't go into the asymptotic region. Yeah, so let us try to cure this. And to cure this, as I said, we should add a constraint that T interaction equals to T, which is equivalent to adding a complex term into the action. And this term is explicitly reparameterization invariant. Besides, the integrand is 0 for flat space-time. So if particles go in and out, the space-time starts from flat and ends up flat. So this integral converges. If particles goes in and doesn't return, the integral doesn't converge. Besides, for simplicity, we concentrated this regularization on one point, R epsilon, which is far away from the boundary. So the particles goes in, crosses this regulator, and now we have 3 regions where the space-time is empty, and the leftmost region is where the space-time is flat. In the rightmost region, this is Schwarzschild with mass m. And if you solve the equations with near this regulator, we get the condition on the solution in the middle region. And solution in the middle region is also a Schwarzschild with mass slightly different from m by a complex factor. Complex because the equations at R epsilon are complex. And imaginary part of mass is larger than 0. And this means that the Schwarzschild radius of this new metric with mass m prime is has complex Schwarzschild radius. So we now live in the complex plane of R, of coordinate of the particle, and particle moves along the real axis of R towards the boundary and outside of it along this contour C. And Schwarzschild radius doesn't bother us at all because it lives in the complex plane. At small energies, it lives to the left-hand side of the boundary, but at large energies, it lives just in the upper half of the complex plane at position with imaginary part proportional to epsilon. And just we start from the trajectory reflecting from the boundary, and we continuously change energy, increase energy of the particle, and we obtain this trajectory continuously and smoothly, which goes under the horizon in the complex plane. So this is a complex solution, and it has correct asymptotics. Let us check what is the result. And we substitute this solution into the action. Actually, this line shows that the calculation is quite complicated. There are many terms in the action. Yeah, so Gibbons-Hawking terms at all infinities, the action of the particle and the initial and final states, so on and so forth. We calculate everything together, and here's the result. And the good thing is that result is it fits in the half of the transparency, so it's simple function of energy of the particle m and parameters of the model, parameter lambda, parameter phi naught. Okay, so here's the result, and the amplitude actually is given by exponent of I times action. Okay, so this is the result for actual result for the amplitude, and I should stress that we calculated not just the modulus of the amplitude, but also the phase of the amplitude. So given the initial state, it's quite simple. There is one initial state and one final state, but we can restore exactly final state given by the initial state by multiplying by the S-matrix element. Phase and modulus. Here the simple graphs of the phase as function of energy and simple graph of imaginary part of action as function of modulus. And actually the probability is equals to 2 e to the 2 modulus of amplitude squared, e to the 2 imaginary part of actions. It equals to 1 if energy of particles is low, and it is exponentially suppressed if energy of the particle is higher than the critical energy, if the energy is enough to form a black hole classically. So at high energies, we can interpret this process that particle collides with the boundary, creates a black hole, and black hole emits a particle again. So the first part of the process is classical. The second part is exponentially suppressed. And one expects that it is suppressed by the number of black hole states to the -1, e to the minus entropy of the black hole. So knowing the result, we can obtain the entropy of the black holes. And this is also the result. The critical mass here, entropy equals to mass of the black hole minus parameter of the model, critical mass, combination of parameters. And this result actually coincides with expressions for the entropy given in the literature. Yes, and I have one final remark about the entropy in this model, and then I will conclude. A remark about the entropy is as follows, that, yeah, there is one particular calculation, Euclidean calculation of black hole entropy. In this calculation, you take the metric outside of the black hole horizon and you continue it to the Euclidean spacetime. It gives you a periodic geometry like a fingertip, and calculating the action on this geometry, you can actually eventually find the entropy. So my point is that the geometry outside of the horizon doesn't know anything about the boundary, because the boundary of space-time that we introduced is inside the horizon. Okay, so it doesn't depend on a particular parameter of the model phi equals to phi naught, where phi naught is the value of the dilaton at the boundary, and therefore we obtain the result which is not the same as in our expression. So the entropy equals to mass, not mass minus a combination, a critical mass, like in our model, because critical mass depends on the phi naught, on the presence of the boundary. So yes, so since our result coincides with some other results from literature, something is wrong with Euclidean calculation. And it seems that this solution, this Gibbons-Hawking instanton, in our model, it doesn't give contribution at all. So, and what does contribution? So let us find another solution which includes the boundaries. So the simplest solution that includes the boundary consists of two fingertips. This is the analytic continuation of the outside of the horizon, of the exterior of the horizon. And this is analytic continuation of the interior of the horizon. And this instanton, this new instanton, includes the boundary which lies in the interior, and it gives the same result for the entropy. So our conclusion is as follows, that this instanton is a saddle point of the Euclidean path integral, and somehow in this model we should require that the boundary is present in all configurations over which you integrate in the Euclidean path integral. In a nutshell, this means that in this model, it is not easy to define a Euclidean path integral. You should just, it remembers the fact that the boundary is present. Okay, conclusions. We actually have a method to calculate the S-matrix elements for very complicated processes where black holes is formed and then it decays into kind of states like Hawking radiation or some particular states psi out. And collapsing solutions do not contribute into this matrix elements. But in simple models, we see complex solutions that do contribute. And in 2015, we used the same method to calculate the scattering of shells in 4-dimensional gravity. And yes, the result was always the same. The modulus of the amplitude was exponent of the minus black hole entropy. And if we manage to generalize this method to field theory, actually, the only thing that we need to do is to find appropriate complex solutions in in field theory. Okay, if we manage that, we'll calculate the S-matrix element between arbitrary coherence states, and this will allow us to check unitarity of S-matrix. And also, my final remark is that there are some replica instantons that give a new expression for the entanglement entropy of the final state, and of this density matrix of the final state to the nth power. And it seems that our solutions should be related to those by analytic continuation. Say if we we take 2n of our complex solutions, which go from initial state to out state, then back, and then n times this way, and continue them analytically, we will obtain, probably replica instantons. But this hasn't been checked. So thank you very much for the attention.
Okay, thank you. Let's see, I don't see any questions, so I'll ask one while we're waiting for other people to generate one. One of the reasons for this decades-long fascination with black hole entropy paradox and the evaporation of black holes has been that there was supposed to be a paradox, number one, and number two, it was supposed to teach us something about quantum gravity. Do you see any evidence of a paradox, number one, and number two, do you see that it has taught us anything at all about quantum gravity?
First of all, we consider a very particular final state. Okay, so we calculate only one element where a particle goes in and exactly one particle goes out of the black hole, and this is a particular matrix element. We cannot judge whether S-matrix is unitary or not. Secondly, we already can see that we restore the phase of the S-matrix, not just the amplitude. And this means that we can connect initial and final states. And this is already beyond the Hawking calculation. Hawking calculation cannot connect at all the initial and final state. Actually, the second message is about quantum gravity. Actually, all this project is about that. So it's just the idea. We cannot say anything about quantum gravity yet, but actually the idea is as follows. If we manage to compute the path integral for gravity and consider it for the processes of black hole formation and evaporation, and find consistent result in some model of quantum gravity and inconsistent result in some other model, that will be like a selection rule for the quantum gravity. Okay, that may lead to requirements that the measure or the action should be formulated in a very particular way. So far, we use the standard calculation with Gibbons-Hawking terms and with standard measure, and we are satisfied with that. We produce reasonable results. But in the future, that can turn out to be a selection rule.
Okay, thank you. We have questions from Valery Rubikov and Luca Buoninfante. So we'll take Valery first.
Yeah, you consider particular final state with just one particle going out. What are other states, and what is what are the obstacles to calculate the amplitude for more complicated final states?
Okay, in field theory, if we consider our particle to be an approximation of a certain state in field theory, in a field theory there are multi-particle states, and you should assume that in a field theory the black hole mainly decays into the multi-particle states. The second approach would be to take this model with one particle, just this model, and say that there is only one quantum particle in the universe. I can imagine two possible final states in this model. First of all, a black hole can emit a particle, it can decay into a particle. Second, the black hole can stay forever, okay, with particle inside. And this could be two different asymptotic states and with different probabilities. Some of the two probabilities should be probably equal to unity if the model is consistent. If the model is inconsistent, then the sum of the probability will not be equal to zero. To unity.
One final state that you're missing in this second case?
Yeah, so we can describe only one final state because we can write amplitude for starting from the Fock space, Fock state of a particle far away, in going into the state of a particle far away. We cannot just formulate the matrix element for the state where the black hole stays forever. So we cannot like calculate directly this probability of having creating an eternal black hole.
So in this particular case, there's no Hawking radiation whatsoever, right?
Well, there is a process when black hole it just emits one particle. So this is kind of analog of Hawking radiation.
Okay.
Okay, next will be Luca, and after him, Alex Vickman.
Thank you. Hello, hi. I have a question regarding the slide number 15, where you made a comment about the Euclidean integral computation for the entropy.
Yeah.
I just want to make sure that I understood. So, yes, this one. So, as you said, like for instance, let's just take a 4-dimensional Schwarzschild black hole, okay? And let's suppose we want to make the Gibbons-Hawking computation for the entropy, okay? So the right-hand side should be just the standard computation, right? Where we consider the Schwarzschild black hole. And we know that from there, Gibbons-Hawking got the area law formula for the entropy, okay?
Yeah.
So are you saying that even in that case, I mean, if one includes the interior, we would get a different result for the entropy?
Look, there is no reason. Okay, so this configuration is more suppressed than the Gibbons-Hawking instanton. It is more suppressed in 4 dimensions, and it is more suppressed in 2 dimensions. In 4 dimensions, it will not give the correct result for the entropy, but this is a more suppressed saddle. In 2 dimensions, I would not include this saddle. I would include this saddle, but this saddle gives incorrect result for the entropy. So my conclusion is that we should reconsider what we call a Euclidean path integral in this theory, because we added a boundary. We cut by a knife the space time into 2 halves. Okay, and probably this configuration, which doesn't include the boundary at all, phi equals to phi 0, doesn't include it. It shouldn't be taken into account in the path integral. We should only take the configurations that include the boundary. And this leaves this makes this subdomain configuration, in fact, a dominant one, the dominant configuration which includes the boundary phi equals to phi 0. And in this case, we obtain the same result for the entropy. So
yeah, so because I think sometimes it's not really clear how to judge which kind of saddle one should include or not in the path integral. So your principle would be like, I include the saddle that contain the boundary. That's what
yeah. So
because,
this is exactly, so this is our basically conclusion that in this model, it is not clear from the beginning what saddle to include. And our conclusion basically is based on the answer, on the result. So,
yeah, because I think even these latest works on the computation, the phenomenon entropy for the radiation, even there, the whole point is to choose one saddle and you get the result. But I'm not really into it, but it seems to be that there is still not a real way to judge and uniquely fix in some way which saddle to choose. Okay, so in that sense, it would be nice to have some kind of better understanding of that.
In the end, we should arrive to consistent formulation of quantum gravity plus Picard-Lefschetz theory, and which will choose for us correct saddles. This saddle is correct. This saddle is incorrect. But at the moment, we do not have a prescription for correct saddles. So in this case, I choose this by hands.
Okay, thank you.
Okay, Alex.
Hi, Dima, very interesting talk. I hope you can hear me. I'm a bit confused. So in one of the most interesting puzzles regarding normal black holes is the presence of the end of time singularity, right? But I presume in your setup, it doesn't play any real role. Am I right?
Yeah. So our solutions go around these singularities in the complex space-time.
So you managed to avoid it.
Basically, my central point was that they managed to avoid the horizon, but actually we start. Yeah, so the trick is that it deforms you in the complex space-time. We start with the usual scattering solution at low energy, which has trivial topology like Minkowski space-time topology. And we deform the solution, and it always remains the solution with trivial topology, okay? What happens is that it avoids the horizon, the singularity, etc., in the complex space-time, okay? Yeah. So
but you see, yeah, it's pretty fascinating, right? Because I have already difficulties to avoid the horizon, right? Because that would imply that, let's say, tunneling would kind of avoid causality, right? Which is a bit
but this is like tunneling. Yes, this is like tunneling. This is going in complex time and in complex space.
Sure. But you see, what I meant is that a normal tunneling still doesn't violate causality.
Yeah.
And
this
that's
thing
why
doesn't. Yeah, this thing should not violate causality. We just calculate the usual path integral.
Okay. Thanks.
Okay, thank you.
Good to see you.
Yeah. Online.
Okay, let's see. I don't see any more questions. Alex still has his hand up, but I assume he's finished asking his question. So if I don't see any more questions, let's thank all the speakers for today's session, and we'll break now and return at 1500 Moscow time for the evening session.